So how do we find those limits that give us an indeterminate form? Now, in the first lecture, we learned some algebraic techniques, but those won't work for all limits. Sometimes the limits can't be simplified algebraically. Thankfully, there's this wonderful thing called L'Hopital's rule. L'Hopital's rule, which is named for a guy from the late 1700s, right around the turn of the century, so like very late 1700s, early 1800s. He wrote one of the first, if not the first, books on calculus. He was helped out by one of the Bernoulli brothers. There's a few of those guys doing their thing. And actually, he was the one that came up with this rule. But I mean, he was paying for everything, so it gets his name. So, L'Hopital's rule. This is a rule that will be tremendously useful for finding limits. It is an extraordinarily powerful tool when you want to find a limit. So here is the rule. So let f and g be differentiable functions on some interval of a, except maybe at a, and assume that g prime is not always 0, although it's okay for it to be 0 at a. If the limit of f over g gives you 0 over 0 or infinity over infinity. That's worth saying again. This rule only applies for 0 over 0 and infinity over infinity. Of those 7 indeterminate forms, this rule can only be used for those 2. But as we already saw, all of those rules are this, so it's all good. But anyways, to finish the sentence, if the limit gives you 0 over 0 or infinity over infinity, then the limit of f over g is the exact same as the limit of f prime over g prime. So essentially, if you're doing the limit and it gives you 0 over 0, just differentiate the numerator, differentiate the denominator, and try it again. And if it gives you 0 over 0 again, you just keep going, and eventually you'll get your answer. Before we try any examples of this, let's do a quick proof. We're only going to prove the simplest case, because this is also true if a is going to infinity. So I'll just write that down too. Also, the limit as x goes to infinity of f over g equals the limit as x goes to infinity. That's a horrible infinity sign. Let me just try that again. Of f prime over g prime. If this original limit gives you one of those two forms. So a could be infinity, or it could be a real number. But this is a hard rule to prove, but let's just do out a proof though, just kind of get a feel for why it's true. We will only prove a relatively easy case. We will only prove the case where a is a real number and where the answer gives you 0 over 0. It's easier to prove and it gives you a feel for it, so we'll do that. So first off, let's set that up. So if the limit gives you 0 over 0, it means that f of a and g of a are both 0. So what we'll do is the limit as x approaches a of f of x over g of x, which we know if we plugged in a into our function right now, it gives us 0 over 0. So we won't do that. Instead, we'll do some algebraic manipulations to this. We'll subtract f of a from the numerator. We'll subtract g of a from the denominator, which we can do because they're both 0. So subtracting 0 won't change our expression. We'll also put f of x minus f of a over x minus a, and we'll put g of x minus g of a over x minus a. That does not change our value either, because we divided both by the same quantity, therefore they cancel out and the expression maintains the same value. But now we have slope, and we know from our properties of limits that we can break up our limit into two pieces, one for the numerator, one for the denominator. And now we have the limit of the slope between 2 points in the curve as those 2 points approach each other. That's f prime at A. That's g prime at A. So we just proved that if the limit of f over g is 0 over 0, that's the same as if you found the derivatives and then plugged A into them.